Now, well, I'm going to introduce you. Well, this time, I'm going to introduce Dr. Aeysha Sultan. She's from Pakistan, and she has agreed to give us a presentation about the work she's been doing for years. She worked at the chemistry department, University of Education, Faisalabad, I think, campus. Faisalabad. I cannot pronounce that properly.
That's Faisalabad. Oh my God.
I'm going to try, and I'm going to learn Pakistani to understand that well.
My God.
And today she's going to talk about synthesis of steroid by radical mediated cascade cyclization. I think that was okay.
Yes.
Well, I would like to acknowledge you, Aeysha, for your presentation. This is going to be on the social media. When this is over, which means Facebook, in YouTube, in LinkedIn. So in all the media we have, and also your presentation is going to be published in our electronic journal. So we will do our very best. So thank you very much indeed. And you have 1 hour, please, and you can go ahead.
Okay, thank you. Thank you, Professor Roberto, for inviting me for this webinar. So as you mentioned, the title of my presentation is The Synthesis of Steroids by Radical Mediated Cascade Cyclization. So firstly, I'll outline the contents, which I will cover. So what's the motivation for this work, objectives or plan of work, and then the conclusion for this work. So the motivation for this work is that why I choose the synthesis of steroids is basically that just steroids are very important secondary metabolites, right? So these are found in plants, animal, insects. A lot of people are synthesizing it because of their role in the physiology and because of their role in our bodies, because the homeostasis which is going on inside all of the organisms is being played by these steroids. So they play the central role in homeostasis, in basically all of the physiological phenomena that are occurring inside their body. Furthermore, these steroids also have tremendous biological and pharmaceutical importance. So I'll highlight a few of the examples of steroids in which they are playing a very important role. So here you can see this is the steroidal nucleus, the four rings, right? So this is basically the steroidal skeleton, and just variation in this steroidal skeleton results in very tremendous change in properties, whether they are physical, they are chemical, or biological. So these two steroids, which you are seeing currently, these have anti-cancer activity. So they are effective as anti-cancer agents. Further, these two steroids, you can see basically the skeleton here. So both of them have anti-HIV activity. So they can be used, or they have the potential to be used as anti-HIV agents. So here we have steroids with anti-diabetic activity, anti-arthritic activity. We have steroids as enzyme inhibitors. So you can see just change in structure, but results in change in activity, right? So these are anti-mutagenic steroids. Then we have heart-related diseases. And these steroids, you can see again, this 4-cyclic system. So this system has the ability to cure heart-related diseases, right? So the steroids are well known for their side effects, such as you can have acne, oily scalp, skin, jaundice, tender rupture, liver cancer, mood swings, delusion, hair loss, high cholesterol, or heart enlargement, etc. But these side effects are associated if you take steroids in excess or if you misuse those steroids, right? So considering the importance of these steroids, I focused on synthesis of steroids. So the previous synthetic approaches, previously different people have synthesized steroids by using different techniques or different methodologies that mainly involve Dehydro reaction, the Michael addition, aldol condensation, or metal catalyzed reactions, and few have also reported free radical mediated reactions. So my focus of this work was to synthesize steroids by using free radical mediated reactions, right? So why we are using free radical mediated reactions is because the free radicals, if a chemist knows, is that they are very selective reactions. We get products of desired quality or the desired products. And these reactions are efficient, they are fast reactions, they are not slow. And most importantly is that free radical mediated reactions favor kinetic products. So if you're a chemist and you know what you mean to be a kinetic product is that mostly what we get is a thermodynamic product. So thermodynamic product is a product which is more stable. But kinetic product is a product which is formed at a faster rate. So sometimes we are interested in products which are not more stable, but instead the products which are formed at a faster rate. So if you're preferring a system that's formed at a faster pace, not the one that's more stable, then you must go on for free radical reactions, right? So these three properties are most important for the free radical mediated reactions. And all of these properties are utilized so far for the synthesis of complex compounds like terpenoids, texoids, steroids. And for the same reason, we also chose the free radical reactions. The next topic is the cascade reaction, because the title says this is synthesis of steroids by free radical mediated cascade reaction. So you have seen what's the motivation for steroids, what's the motivation for free radical, and lastly is the cascade reaction, right? So cascade reactions are also known as biomimetic reactions. They are also called zipper mode reaction. They are also called domino reactions. And what are these reactions? A cascade reaction is basically a sequence of reaction that once initiated goes on its own, right? And since you know that if you have multiple reactions, and if you can carry out all those multiple reactions in a sequence, so you just save your time, you have the economy of time, and you have the economy of reagents, so you save money as well as energy. So just to demonstrate what's a cascade reaction in a pictorial form, just consider that if you have blocks, right? And you have placed those blocks side by side, just like that, and just give a stroke to the first box. You can see that first box will topple down, and with it, all of the blocks will topple down itself. So just like that, cascade reactions are like that. You just have to initiate the reaction once. So once you initiate the reaction, all of the sequence of the reactions will go on its own. So that's why we have chosen cascade reaction, because in this way we will plan to save our time, to save our money, to save our reagents. So free radical reactions have been used in synthesis, and I'm here quoting an example of free radical mediated synthesis of steroid. So here you can see this is an open chain system, and here we have a carbonyl with an alkyne, and here we have an iodine which is at, you can say, at beta position to an unsaturation. So here in cascade reaction, since we are using free radical mediated reaction, we will first generate a free radical. That free radical will undergo cyclization to this alkyne, and this alkyne will promote the cyclization of the second ring. So we'll get two rings in just one step. And you can see also that the stereochemistry of the products is also well defined. So we are getting a selective product, we are getting cyclization of two ring system in just one step. So this is a very big achievement. So whenever you are carrying out a free radical mediated reaction, we need a radical initiator and we need a radical source. So basically, this is our radical initiator. This is aza bis isobutyronitriol, and we are having this is tributyl tinhydride, right? So this is basically our source of radical, and this is the radical initiator. And the solvent we normally prefer is benzene or any other solvent which is more stable. So normally we prefer benzene as a solvent. So this reaction is an example in which we can carry out the synthesis of steroids by free radical mediated cyclization. So the summary of work which we did is that we need to have a system like that, right? So if you see this system, so we have an alkyne on alpha carbon, and to this beta carbon, we need to have a vinyl halide. So all of our systems which we used in this study, they consisted of these two systems. So we need to have an alkyne system, and we need to have a vinyl halide here. And what will we do is that we will use the radical initiator and the radical source, which is tributyl dihydride, right? So this tributyl dihydride will do what? It will abstract this bond, it will break the bond between carbon and bromine, and will generate a free radical here. So this free radical, which is vinylic in nature, is highly reactive. And the next comes our second reactant. So this is a cyclohexenone system or cyclopentanone system, right? So we need to have an unsaturated ketone, alpha beta unsaturated ketone here. And this vinyl radical will add up to this system, right? Like this one. And then this 5-member ring, which has become a bearer of the free radical. So this will add up to this alkyne. So we need to have an alkyne which is close to this system. So when these two systems are close enough, so what will happen? So we'll carry out the ring cyclization. So that's why we are preferring to have an alkyne here, alpha carbon, so that the free radical becomes in proximity to this alkyne. And we need to have a vinyl halide because the vinyl halide bond is very much labile. So it can cleave easily, and the radical, which is highly reactive, will promote the reaction. So we can have a system like that one, and the product which we will get, you can see here, this alkyne will become converted into this alkene with the radical, right? And after quenching the radical, right, we have to quench the radical. We have to stop the radical from taking place further so that we do not get any further side products. So we quench this radical, and like this one. So the radical has been quenched, the radical reaction is stopped, and then we isomerize this double bond. Right, so you can see this double bond is outside the ring. So if a double bond is outside the ring, this is unstable, but we need to stabilize that. For that purpose, we isomerize this double bond so that it goes inside the ring. So double bond, which is endocyclic, which is inside the ring, is more stable. So this was our summary of work. So we need to have structures which are having a vinyl halide and which also have an alkyne alpha to this vinyl halide, right? So this was firstly our model study. So in order to carry out the model study before applying it to complex system, so we carried out the retrosynthesis. You can see here. So this is not a 5-cyclic system. This is a 3-cyclic system. So we say this is a steroids because the A ring is missing here. Right? So if one of the ring of steroidal skeleton is missing, we say it as a steroid. Since the A ring is missing, so we say this is a steroid, right? So when we carry out the retrosynthesis, we can get two synthenes, right? So we can have a alkyne system, which I was referring to. We must have an alkyne alpha to this vinyl bromide here. So upon further retrosynthesis, so we get this reactant, right? So it means that when we have to carry out the synthesis, we need to have this reactant. All right, this is a ketone and it's alpha beta unsaturated, having a bromine at alpha position. So we need to have this vinyl bromide containing cyclohexenone. So when we carried out the synthesis, the plan was that we will start with the cyclohexenone. We'll carry out its bromination at alpha position. Further, what we'll do is we will carry out the 1,2 addition on this carbonyl. So we'll use this alkyne and treat it with N-butyl lithium, right? So this N-butyl lithium is basically a base, and that will abstract the proton from this hydrogen, from this alkyne, right? It will convert it into a strong nucleophile, and the nucleophile will add up on this carbonyl. So here we are having a alkyne, which is next to the vinyl system, which we were planning. And next we will react it with a cyclohexenone system. right? So cyclohexanone is our second reactant, and the cascade reaction between this system, which is basically an alkyne containing vinyl halide, and the cyclohexanone will result in cyclization of this aromatic system, of this steroidal skeleton. So this was the plan, and let's see how the plan worked. So we carried out the synthesis of this vinyl bromide. The reaction went well, and the product was 85% yield. The next step was to convert this system into this, say, alkyne containing vinyl bromide, right? So we carried out different reactions in order to get the product. So when we use sodium acetylide, you can see, so without any base, because sodium acetylide is itself a strong nucleophile, we didn't got any product, whatever the equivalent we used. But then we changed the reactants. So instead of using sodium acetylide, we used trimethylsilyl acetylene and treated with N-butyl lithium. And strangely, instead of getting the desired product, we got the cyclohexanone itself instead of the desired product. So the blue color reactants actually are representing what we actually got, and the black color was what we were planning, right? So we actually got the cyclohexanone instead of the desired product. What is happening actually, the N-butyl lithium, when used in slight excess, it causes translithiation because the halogen is replaced with lithium. So that was the reaction which was being carried out. So instead of this, instead of using N-butyl lithium, we used LDA, lithium diisopropyl amide. It's much more stronger base. So when we used LDA in such situation, we got the product. So we got two products depending on the substance. If Y is trimethylsilyl, we got 60% of the 65% yield. And when it was phenyl, right, it was phenyl acetylide, then in that case, the yield was 90%. So we have so far found out that when you are carrying out 1,2 addition to an alkene system, to a carbonyl system of nature like that one, so you must prefer LDA instead of using N-butyl lithium, because N-butyl lithium preferentially carries out lithiation, translithiation, instead of carrying out the 1,2 addition. So the confirmation of the formation of products came from the NMR of the two reactants, of the two products. So once we carried out the synthesis of this vinyl bromide, you can see this beta proton appeared at around 7.4 ppm. Right? This is highly downfield value because this is beta to a carbonyl system. But once you destroy the carbonyl system, the value should not appear that much low. So once we have destroyed the carbonyl system by attachment of this alkyne to the alpha position, then you can see this proton, which was previously appearing at 7.4, this is now appearing at around 6.1, right? So this is confirmation of successful alkynation. Furthermore, we also got the appearance of this, you can say, the phenyl protons, which is confirming the attachment of phenyl to the system. So next step was to protect this OH, because we don't want here this hydrogen. If this hydrogen is present here, it will interfere in the further reactions. We need to have this hydrogen protected. So we prefer to protect it with a methyl group. So for that purpose, again, we have tried different reaction conditions, and butyl lithium didn't yield any product, which we are thinking is because of this translithiation. LDA, if you are using in THF, this didn't yield any desired product. Instead, we got a large number of products on TLC. Then we tried another reactant, which was much more feasible. So we have used sodium hydride and we have used dimethylformamide. So this is the best condition for this reaction. So we have carried out this reaction at room temperature instead of carrying out at minus 78 degrees C. And the desired product was obtained in 66% of yield. Fermentation pattern, which is confirming the formation of this reactant. So with successfully synthesizing of this synthone, which was our major key reactant, the next step was to carry out the cascade cyclization. right? So here we have the vinyl bromide, and here we have the alkyne at desired position, and now we have to carry out the reaction. So once you are using THF as a solvent, and we are using N-butyl anhydride in AIBN in 1:1, we don't get any product. So we suspected that maybe AIBN is in excess or the tributyl anhydride is in lower amount. So we changed the ratio. So we used 1.5 equivalent of tributyl anhydride with 0.1 equivalent of AIBN using benzene as a solvent. So we got the desired product, but with 10% yield. We increased the amount of N-butyl anhydride, and AIBN was retained 0.1, and benzene was used as solvent. And after fluxing for 14 hours, we got the desired product in 69% yield. And if we further increase, if we change the solvent to THF and the many conditions are retained as such, no product is obtained. So this condition is confirming that if you are carrying out the reaction for the free radical mediated cascade cyclization, you need to have solvent of benzene. You don't need to have low boiling solvent like THF. So if you're using low boiling solvent like THF, so your reaction don't get well. So we need to have solvent like benzene. So it gives more product. So this is basically the mechanism of what's happening. So this is basically the AIBN. When we heat this reaction, so the nitrogen is excluded and we get two free radicals of this as a isobutyronitrile. And this is basically the isobutyronitrile radical. This radical is actually the initiator of this reaction. It will abstract the proton of this dibutyl anhydride, and this is the tin radical, which will actually carry out the reaction. So this tin radical will abstract this bromine, and the bromine will cleave and will generate a vinyl free radical. This vinyl free radical will undergo cyclization, right here, and this radical will come here, and this has a triple bond in its very proximity. So this will add up to this triple bond, and we'll get this product, right? We'll get this radical, and we have a double bond, which is exo with radical. Here, the quenching of this radical with tributyl anhydride will result in destruction of the radical, and we'll get the product 5. So when we carried out the spectroscopic analysis of this product 5, what we got is that we have a double bond, which is endo, not exo. And how we confirmed it? Because we got a CH2 here. So the appearance of this CH2 suspected that this double bond has isomerites. So this spectroscopic evidence indicates that actually the product that we got, that we were expecting to have an exo double bond, is actually basically a product with an endo double bond, because the endo double bond is much more stable. So this model studies successfully concluded, and this is the mass spectrometric evidence, which is indicating the successful formation of the product. So here, the conclusive evidence of the presence of the endocyclic double bond came from the exclusion of this benzyl fragment, which gave 874% excess, right? So this fragment at 91, that was confirming the presence of this benzyl fragment. So this is the conclusive evidence of successful model studies. And this is the mechanism for isomerization. So once we get this free radical here, so what happens that this, after quenching of this free radical, it undergoes isomerization under heating conditions here. So one is that we can just think of the thermodynamic product. So that's going on to isomerize under free radical conditions, under heating conditions. And the other mechanism which is possible here is the 1,3 sigmatropic shift. So here you can see that we are having an alpha proton at this position, so consider it as position 1, and this free radical will shift from this position to here. This is a shifting of proton along with shifting of this double bond, and further the quenching will result in formation of this radical. So this is basically the mechanism for isomerization of the product. So once the model studies were completed, next we carried out the synthesis of estrogens. right here. So estrogens are unique in a sense because they have a ring as an aromatic ring. So this is basically our system. Again, we are having a system in which we need to have a vinyl halide, and next to it must be an alkyne system, right? And we can get this system from this type of the cyclohexanone, and we are having bromine here and with a benzene like that one. So this system can be easily obtained from tetralone. So this is a very commercially available reactant. It's very cheaper, and we can use this in a very easy way. So this was our synthetic scheme. Firstly, we will bring in vinyl halide here. We'll carry out the 1,2 addition to this carbonyl, and the same chemistry will repeat as was mentioned in previously. So once starting with this tetralone, we prefer to firstly derivatize the aromatic ring to bring the substituent on the aromatic ring. So when we tried to carry out the bromination of the system, to derivatize the system, to aromatize the system, right, to bring substituent of nitro group. So we use different conditions, and the different conditions as mentioned in the table yielded different products. So we have seen that if we are getting out reaction at low temperature, or if we are using chloroform as a solvent, we can control this desired product. We can get the desired product of 12 and 13. But if the concentration of the acids is higher, if we are using excess of nitric acid, or if you are using excess of this sulfuric acid, and if you are heating the reaction, in that conditions, we get some products which were not desired, but they were very interesting. So we have also found it from these studies that the system of tetralone, although very attractive, it's very much prone to aromatization. Right here, instead of having the nitro groups on the aromatic ring, we got nitro groups on the aliphatic ring, which was also aromatized. So we got a lot of, you can say, naphthol, substituted naphthals in these studies when we were using tetralone as a substrate. And the most interesting product was this coupled product. This is basically a 15 system. And you can see here that we have combined, or we have joined two tetralone system together. And this is the XRD structures for those unexpected products. Here we are having two nitro groups on this naphthol system. So the tetralone got first aromatized, and the nitration occurred on the phenolic ring of the naphthol system. And here we are having the two rings of the tetralone which are joined together. So one thing we got from this, that instead of carrying out the derivatization of the tetralone, we must use the tetralone itself instead of carrying out or wasting our energies on this derivatization strategy. So the next was to convert this tetralone into an enone system. Right, again, the dotted arrows are indicating the reaction didn't work, went as we planned. So we carried out the firstly enol trapping reaction by using benzyl chloride. So we treated the benzyl chloride and sodium hydride with the tetralone, and we expected to have this O-benzylation. And further, the oxidation with DDQ in presence of HMDS was expected to yield the enone. But instead of that, we got the benzylation at the alpha carbon. So this is O-benzylation, and this is C-benzylation. So what we got was C-benzylation, and this reaction is not a success, right? So this strategy was not success, so we thought of alternating strategies. So this is evidence of C-benzylation. So you can see here, there is an appearance of an extra CH2. This extra CH2, you can see here, the C1 prime. This is indicating that we are having a C-benzylation instead of any O-benzylation. So instead of carrying out with the benzylation strategy, we switched on and we changed the strategy, and we thought that we will carry out further first alpha halogenation, and then we will carry out the dehalogenation, dehydro halogenation. That way we can get a double bond here. So the alpha halogenation was carried out by different reactants. All of them yielded very interesting ratios. So we got, if you are planning to have an alpha bromine or alpha iodine, you can see that we can have the, we can use, make use of NBS and butyls and bromosuccinimide and in chloroform. So in just 2 reactions, you can have 80% yield of the desired product. And you can also have excess 88% yield of the alpha iodo product if you just reflux the iodine in presence of acetic acid and chloroform as a solvent for 28 hours. The reaction is very reversible, but once you get the product is in good yield. We get 88% of this alpha iodo product, and we got 80% of this bromo product. And if you are using acetic acid as a solvent and you're using bromine, then we only get this product in 98% yield. So we have 2 bromos at alpha carbon. So all of these reactants were very important to us. All of those reactants can be used in the next step, which is the dehydro halogenation. So we carried out dehydro halogenation of the substrate using triethyl amine, and in all of these cases we got aromatization. As I mentioned earlier, the problem with the tetralone is that this substrate is very much prone to aromatization. Yeah. So we changed our strategy, and in this strategy we said that instead of carrying out the dehydro halogenation, we just carry out direct 1,2 addition on this carbonyl system, right? So in that case, we will have an alkyne next to this alkyl halide. So we are not having a vinyl system here, but that'll work because since the carbon halogen bond is still labile, we can have a free radical here. But when we tried this reaction, again, we got the naphthol as the only product. So again, the reason was the labile nature of this tetralone, that's very much prone to aromatization. So here we predict that actually the acetylide, which we were preferring to appear as a nucleophile, it's actually acting as a base and abstracting the proton and getting out this aromatization here, right? So instead of using the alpha monobromo ketone, we then tried to use dibromo ketone here. So here we thought that in case if one of the bromine is lost, still we will have 1 bromine and we'll have the enonic system. So once we tried the strategy, again, we got the aromatization product. This time it was 32% of the bromonaphthol, and we got 52% of the desired product. So at least we got the desired product, which was confirmed by different spectroscopic evidence. The next step is to protect this OH group. So once we try to protect this OH group, again, we faced the failure of the strategy. Instead of getting the desired product, we got 2-hydroxy in the subsystem, which resulted in the failure of this reaction. This 26 product having 2 hydroxyl groups, this is not a suitable reaction, and we ended up this strategy because it's of no use. Right here. So we also tried to carry out dehydrogenation of this product, dehydro halogenation of this product, and here you can see that we are having the 2 bromines here. This is the spectroscopic evidence of formation of those products. So this is our reactant 23 having 2 bromines, and here this is our product, which is clearly indicating presence of single bromine because the 2 bromines are appearing in 1:1 in the high resolution EIMS here. So skipping the mechanism here. So again, we used another strategy. Instead of using tetralone, we used naphthoquinone as a system because in it, we already have an enone and an extra carbonyl. So if we can protect the carbonyl, we can go on for this system. So once we tried to protect it with ethylene glycol, the reaction was a failure. So we could not use it as such. Then we tried to carry out the use of 1,2 addition with methyl magnesium halide or any other Grignard reagent. Again, that was again a failure. So again, we dropped the strategy of using 1-naphthol as a system. So here you can see that we got this 1,2 addition, but the reaction didn't go on very well. So instead of using tetralone, which is prone to aromatization, we then switched over to indenone system as an alternate to tetralone. Again, the strategy was the same. So we carried out the halogenation followed by dehydro halogenation. So we got 39 as our product. Also, we got the enol trapping reaction using trimethyl halide, and further the reaction with DDQ and HMDS resulted in formation of the desired product, which is 39, and the yield was not much good, but again, we got 39 as the product. So this was a bit success in this reaction, right? So here is a spectroscopic evidence for having bromine at alpha position and bromine at beta position. So we got both of these products as such. And we then synthesized the dibromoindenone system because we can easily halogenate this product. So the yield was very high. You can see the XRD structure, the C13, and the high resolution ESIMS of the product. So all the reactions went on quite well. But here we can see that when we carried out the hydrohalogenation of this dibromo product, we got 39 here, this product, in only 5% yield. So this is not a successful strategy. So the reaction was not a success here again, because the yield was very, very poor. We cannot continue with this reaction. Again, the other strategy was to carry out direct addition to this dibromo system. And when we carried out the addition of estrolide to this dibromo system, we got only one product, that's 41. So here again, you can see that in that case, we are not getting any dibromo product. We are not getting any 1,2 addition. Instead, we are having the substitution of the bromine with the system, and we are getting a conjugated styrene type system instead of the desired product. So this reaction also didn't work well for our system. So this is the spectroscopic evidence. You can see easily these are the two alkynes. There are two olefinic double bonds, olefinic carbons, and you can see here the benzene ring, and this is the low resolution mass spectrum of the same product here. So another system, we tried a second approach. In that case, we will carry out the direct 1,2 addition on this ketone, and then we'll carry out the dehydration of the system. Then we'll reduce this triple bond to double bond to yield this type of system, and then we'll carry out the free radical mediated cascade cyclization. So with this strategy in mind, we carried out the 1,2 addition, and here you can see we'll get this propylic alcohol type system, and upon dehydrogenation, we'll get this system and so on. But the system didn't work out at all. So this reaction went well up to 45. We got this propylic alcohol, but the further dehydrogenation yielded unidentified products because there were quite a lot number of products. We preferred to drop the strategy as well. So in another strategy using the tetralone system, what I got is that we have tetralone will carry out condensation with an aldehyde to form a chalcone type system. And this chalcone will have a halogen here, all right? So we, instead of using the vinyl halide, we are here using an aryl halide here because the reactivity is comparable, and we'll treat it with the conjugated system, and we expect it to have this type of system. So with this strategy in mind of using these two reactants, which was entirely a different strategy, so we carried out the synthesis of this system having an halogen at this position, or the position to this double bond. So the reaction yield was quite high, but when we carried out the conjugate addition of the unsaturated system, the reaction didn't work well. So this is the synthesis of the chalcone system having halogens. You can hear this is our most interesting product because we are having a chlorine here on this position. So this is the most suitable position for the reaction. And next you can see here. So this is a mass spectrum, quite interesting because in this system we got something like that. So this was also a published work of ours, and it was focused on mass fragmentation pattern. So here comes the intramolecular, so free radical mediated intermolecular cyclization. And this was our strategy. We must have a halogen here, and conjugate addition of this system will yield this 49, and the 49 will further condense to form this steroidal skeleton having an additional ring. with this 5-membered ring here, right? But once we carried out the reaction, we got different products. First was the 51, right, in which the halogen was removed. Second, the product in this case, we got the conjugate addition, but no successful reaction of cyclization was continued. We just only got the conjugate addition. And in the next one was we got nothing at all, right? So this reaction of intermolecular cyclization was not a fruitful strategy as well. So these are the different spectroscopic evidence of this reactant. You can see here there's double bond, but in the product, we have reduced this double bond. So this also indicated that we can carry out the reduction of carbon-carbon double bond in free radical mediated condition. This is successful conjugate addition, but the reaction didn't work well because we were planning to carry out 2 steps in a single part. So this is only conjugate reaction. So no reaction went over further. So with tetralone strategy was not much a success, we turned to our third type of synthesis of active steroids. So active steroid is basically a steroid skeleton of beta-toxinin A, right? So again, this was the retrosynthesis, and the important thing is that we must have a vinyl halide here and must have an alkyne here, right? So we need to have 2 systems. The rest is some auxiliaries, and they impart different biological activities here. So in order to carry out this reaction, firstly, we synthesize the substrate 58, right? And for that purpose, we use this system, which is a methyl substituted cyclohexanedione. And we carry out conjugate addition with this methyl acrylate, and conjugate addition resulted in this product. You can say this is a tri-ketone. The cyclization of tri-ketone resulted in 58, and the selective production of this 58 resulted in the 64, which was our desired product here. Right. So this 64, once we carried out the enol trapping because we want to synthesize this reactant of ours, in which we need to have a vinyl halide here. So reaction was carried out very successfully. We carried out enol trapping with triethyl salyl chloride in presence of LDA as a base at -78 degrees C. The yield was 63%. And then oxidation of the substrate with DDQ and HMDS at room temperature, followed by halogenation and dehydro halogenation, resulted in formation of 57 and 54% yield, which was quite reasonable. The next step was to carry out the 1,2 addition. So 1,2 addition was again carried out quite successfully using lithium trimethyl substituted alkyne, and the reaction went well at -78 degrees C. We got this reaction, and then further this intermolecular cyclization resulted in this cyclic ether here, right, which was our desired substrate. So this is our key reactant, and we are having the alkyne and the vinyl halide at the correct position here. So you can see here the stereochemistry of acetal formation. So when we are carrying out the acetal formation, and here you can see that this hydroxyl group of the alkyne is in a perfect position to attack on this carbon, which is protected by the cyclic acetal right here. So in this way, this oxygen is protected, and we get intramolecular acetal formation here. Right. So this stereochemistry is actually controlling the stereochemistry of the acetal. So with this acetal in our hand and the alkyne in perfect position and the bromine at perfect position as well. So we are having a vinyl bromide and an alkyne as well. So we carried out the intermolecular cyclization, the free radical mediated cyclization. Right. So when we carried out the intermolecular cyclization between the cyclopentanone and the system, what we got is we got 70 and 15% yield. So we were expecting that we'll get this 5-membered ring to 5-membered rings, and then we can isomerize this exocyclic double bond to yield an endocyclic 55% yield. 55. But instead of that, what we got is that we got the conjugate addition, but the hydrogen of this terminal alkyne was substituted with tributyl dihydride, tributyl tin radical. So this is basically the radical quenching. So this reaction only yielded 70 and 15% yield, but we didn't got the actually desired product. So this reaction also yielded all the interesting results, but the desired results were not obtained here as well. So the mechanism of formation of 70 is that, so once we are having a vinyl bromide and an alkyne at the correct position, and we carry out the radical reaction, the first step is the generation of the free radical here. This free radical will undergo the conjugate addition here, and further, the cyclization was supposed to occur, but here what happens is that this free radical is actually quenching, is actually trapping this hydrogen here, right? The hydrogen is actually shifting on this alpha position, and the free radical thus formed on this alkyne is being quenched with tributyl tin radical. So we are having a tributyl tin on this terminal position here. So this is the reason why our strategy failed. So further, if we increase the concentration of this alkyne, of this reactant of ours, considering that if we increase the concentration, maybe the reaction worked well, but instead of that, if we increase the concentration again, we get the dimerization product instead of the desired product. Right, so the increasing concentration of 56 also yielded futile results. Instead of desired, we got 71, which is an isomerized, which is a dimerized product actually. So the mechanism is that once we are having a free radical here, which is the start of reaction, the free radical undergoes the reaction with this alkyne, and we get an alkene from alkyne here. So this is the mechanism of dimerization of the product here, right? And if we increase the concentration of tributyl tin hydride, in that case, get simple removal of the halogen straight away from here. So no cyclization is occurring. So now we have the conclusion here is that in model studies, we got the desired product because the alkyne was not having a terminal hydrogen, right? So if you are carrying out the free radical mediated cyclization for synthesis of steroids on such systems, you need to have a no hydrogen on the terminal position. If you're having a terminal hydrogen here, so your reaction will not go on fine. Further, if you are trying to use the tetralone or the analogous system, again, your strategy will not work well. These are our findings for free radical mediated steroidal systems. Thank you.
Okay, thank you very much indeed, Aeysha, for your nice presentation. And well, you would like to say something else about the work, your future plans? You're more than welcome to do so. Please go ahead.
Okay, so after carrying out this work, which was very extensive, I have thought about switching the field. And, you know, sensors are very interesting for me because not only because you can just make some complicated structures, because it gives you the freedom to think independently. Because when you are a synthetic chemist or you're carrying out the synthesis, you just feel as if you're creating something. So currently I'm working on synthesis. And I'm working on synthesis of small molecules instead of with complicated molecules. So currently I'm synthesizing some heterocyclic systems. I'm synthesizing conjugated systems like chalcones, porphyrins. Also, I have started working on the synthesis of the preparation of the heterogeneous catalyst that can work well for synthesis. And also I've made some changes in my field, and I've started working on bioplastics. So currently all of these works are going on in parallel with some nanomaterial also in the bucket. So currently I'm working on these fields, but still my interest in synthesis is quite huge because, you know, it gives you the freedom, it gives you the confidence that at least you're creating something and you can make anything you want.
Well, that's very good. And tell me something. Do you have any plan for the future? Are you planning to go abroad to do something else?
Yeah, well, I'm thinking of, and I'm strongly planning to go abroad so that I can see how we differ in their strategies, because in Pakistan, what our strategies are, we're not much on the applied side, and we are lagging behind technologies. Just I want to see how they are working, what's the difference between our thinking and their thinking, and how we can just translate and transfer their strategies and their technologies so that we can work for betterment of humanity and betterment for economy of a country as well.
Tell me something, which places are you planning to go, or you would like to go?
Oh, I don't have some preference. You can say just you can say technologically advanced countries, which are ready to accommodate and which have facilities. They can accommodate people like us. So in general, I don't have any preference for a specific country.
Do you at the university where you work for, is there any chance of getting this pay leave and go somewhere else for, say, a year or two to carry on more research?
Well, as such, there is no restriction, but currently I'm on TTS, tenure track system. So you need to have to pass, say, midterm review after that. There's some limitations. So once these limitations are over, so there's no restriction. My family university, that they definitely favor if a person is interested in going further in the research or in our studies.
Is there any group all over the world which you would like to visit and to stay there for a while? Any research?
It must be Chile then.
Yes.
It must be Chile because Chile is very beautiful. I want to see how beautiful
Here
places.
you will be more than welcome, actually. Well, we need to work on that, and I think it's going to work. And it will be a pleasure to welcome you in Chile. Chile is a beautiful country, and you will find all the facility here to carry on your work.
That would be great. That would be wonderful.
Very well equipped lab all around,
Yeah.
all around the country. They are good scientists. They are very good people like at organic chemistry and synthesis of these rather complex systems and molecules, which I call them macromolecules and that kind of thing.
Yeah.
Are you planning to get involved deeply in nanoparticles and that kind of an application of that in the future?
Yeah. That's it. Actually, I'm quite new to nanoparticles, and I'm just exploring that. So I'm not too much expert in that, but I've started to explore the field very recently, and I've started work, and the work is very, very interesting indeed.
Well, you see, in Chile, we have a scheme which you may use, and you can apply for a postdoc fellowship in Chile, and it will give you enough funding for you to stay in Chile and to live properly, and to carry on your research. So this is something that we need to plan for this year by June, July, no later than that. So that would be absolutely wonderful if you could come over. Well, I say so because you're a young scientist and you have a very, very lovely future. So it's something that you just need to push.
Oh, that's great.
To move
So the
forward.
compliment.
But you see, restriction, we have restriction everywhere. The world without restriction is not a world, it's something else. But the important issue is that we have to overcome those and to be happy. And when people do research, they are happy. That is the important issue. Well, Aeysha, please, my regard to your colleagues, your family, and please let us keep in touch and don't forget the 2 articles.
I will.
I'm going to be ringing you up almost every second.
And I told you the strategy, you must start scolding me. If you don't start scolding me, I won't work.
Well, it's not,
I
as
just
I said
forget.
to you, I'm going to travel all the way from Chile to Pakistan and stay by you and say, Aeysha, you cannot forget this. It's very important. The whole day and night, you will be able to sleep. So, my dear friend, a great hug to you, your family. My love to your parents and brother and sister.
I welcome
And
it.
all the very best to the people in Pakistan, which are very, very nice people. So all my love and affection to you all. Thank you very much. And
thank you very much.
We are going to be in touch. Bye, my friend.
Bye. Bye. Thank you.
God bless you. Bye. Bye.
You
Bye.
too. Bye. Bye.